So Hagen-Poisson law gives the equation which relates flow rate with parameters such as viscosity of the fluid, pressure, diameter and the length of the capillary tube. So in the Hagen-Poisson law, we have considered capillary tube, the flow between the capillary tube, and we have derived for the flow rate. So here we will be considering flow between parallel stationary plates. Instead of tube, here we will be considering the parallel stationary plate. Okay. So when the flow occurs in between parallel stationary plates, something like this. Okay, if the flow occurs, what could be the expression to determine the flow rate? That is what the derivation. So here these two are the parallel stationary plates considered, and a small elemental fluid is considered in between, something like this, of length dx. Okay. So this is the front view and this is the side view of the said front view. Okay. Again, the procedure, derivation procedure is exactly equal to the Hagen-Poisson law, where the procedure you have adopted to derive for the flow rate in capillary tube, the procedure remains the same. So you will be considering the equilibrium equation, and for the equilibrium equation you will be considering the force, pressure force along left hand end and along the right hand end, then the shear force, then you are going to apply equilibrium equation, then you are going to apply Newtonian fluid concept, then integrating, and at the end you are going to get the maximum velocity and the flow rate expressions. So this is the procedure. Again the same procedure is followed here, only thing is the area. In the tube, the area being pi d square by 4. In this case, the area being length into breadth. Okay, that is what the difference, only difference. So here also considering the pressure force at the left hand end. So the pressure force at the left hand will be pressure developed in the left hand end multiplied by 2y into b. Here 2y into b is the area at the left hand end. So this amount is y, from this point to this point, half part is y. So from here to here it will be 2y. So 2y into the b. 2y into the b is the area at this point, this point. So it will be the side view point, side view section. So pressure into area gives you the force. Similarly, pressure force at right hand end, d minus p minus dp. P minus dp. Again there will be decrease in the pressure which is assumed. So p minus dp will be the pressure at the right hand end. 2y into b is the area. So pressure multiplied by area, you will get the force. Similarly, shear force. Shear force will be developed along the circumference of the fluid considered. Sorry, not the circumference, along the surface of the fluid considered. So this is the shear force expression. Tau is the shear stress multiplied by 2b into dx is the area. 2b into area. 2b means 1b and another b. So 1b for the surface of one plate and another b is for the surface of another plate. There are two plates considered. So two surface are in contact with the fluid. Therefore here it is 2b multiplied by dx is the depth, this one. So area multiplied by shear stress gives you the force. Considering the equilibrium equation, algebraic sum of all the forces in x direction will be equal to 0. So if you substitute all those things in the equilibrium equation and if you simplify it, you will get dp is equal to tau into dx by y. You need to simplify this one. I have not simplified here, you need to simplify this one. Okay, you will end up with this equation, call this equation as 1. Next, according to Newton's law of viscous flow, we know that tau is equal to minus viscosity into du by dy. You call this equation as 2, y minus, because as length increases, the velocity decreases. Look at here, as y increases, velocity decreases. Here it is 0, here it is 0, at the center it is maximum. Therefore, minus is considered here. Substituting 2, this one in 1. So here tau term is there in the first equation. Substitute for the tau term, this one. You will get dp is equal to minus viscosity into du by dy into dy by dx by y. And if you still further simplify it, you will end up with this equation. Call this equation as 3. Now in this equation you can observe dp by dx, where dp by dx is nothing but the pressure gradient, and which is considered to be constant. So integrating this expression, because du term is there, if you integrate du, you will get mu, that will be the velocity. Okay. So integrating du with respect to y, something like this, integrating du into integration of the right hand side, integration of the left hand side and integration of the right hand side, and if you simplify it, you will end up with this equation. Call that equation as number 4, where you will find some constant c, which is integration constant. If you integrate any constant, you will end up with the c plus c constant. Anytime you will end up with c. So applying boundary conditions. So applying boundary condition, again to know the value of c and then substitute back in this equation. So applying boundary condition at y is equal to plus or minus h by 2, u is equal to 0. That is the boundary condition, because look at here, y is this amount, y. If the y is plus h by 2 at this position, u equal to 0. At y is equal to plus h by 2 at this position, u is equal to 0. So if you consider y is this amount, if you consider y at this plus h by 2, 0, minus h by 2, the velocity will be 0. That is what the boundary condition considered here. So equation 4 becomes, now if you apply this condition in equation number 4, equation number 4 becomes something like this, where c, for c, if you apply boundary condition, you will get the value of c. So substitute 5 in 4. Okay, substituting this 5 in 4, you will get the sixth equation, that is this one, u is equal to 1 divided by 2 eta into dp by dx into h square by 4 minus y square. So this is the expression for the velocity distribution in the flow between two parallel plates and is parabolic in nature. As you can see the expression, we can conclude that it is parabolic in nature. Okay. Then the maximum velocity, this is velocity at any point between 0 to h at any point. If you want to maximum velocity will occur at y is equal to 0, that means at the center. At the center, if you consider y as 0, at the center the velocity will be maximum, as you can see here, because you know that velocity is parabolic. Velocity is parabolic, so it will start with 0, it will take a curve and end up with 0. It is parabolic in nature. That is what you can observe in this equation. So since it is parabolic, at center y will be equal to 0, therefore u will be equal to 0 at center. Therefore if you apply this condition to equation number 6, you will end up with this one, u max is equal to h square divided by 8 into eta multiplied by dp by dx. Okay, this is expression for the maximum velocity in the flow between parallel plates. Now for the pressure difference, if you consider P1 at the left hand side and P2 at the right hand side, the pressure difference, if I consider as P1 minus P2, if I consider dP is equal to P1 minus P2, and since I have considered the entire length of the member P1 and P2 and entire length, dx I will replace by L. So you can rewrite this equation as u max is equal to h square by 8 eta into P1 minus P2 by L. So this expression you are going to use in the numericals to solve the problems. Then after calculating the velocity, try to calculate the flow rate, because that is what we need to get at the end. So flow rate will be given by velocity into the area. So dq, d is for elemental fluid, what we have considered. So dq is the flow rate at that particular elemental fluid, but is equal to velocity multiplied by dA, that is area of the elemental fluid. So area of the elemental fluid considered will be 2b into dy, 2 into b into dy. U is this one, that is what we have derived here, equation number 6. This is u. U will be multiplied with this area to get the flow rate. Okay. So if you substitute u and dA in this equation, if you substitute u and dA in this equation, you will end up with dq is equal to so and so, this expression. Now this is dq. If you integrate this expression with respect to again y, you will end up with q, that is the rate of flow is equal to certain value. You need to integrate this equation now. So if you integrate dq with respect to y between the limit 0 to h by 2, because at h by 2 we know that the velocity will be 0. So between the limit 0 to h by 2, if you integrate, then dq, integration of dq becomes q is equal to integration of the right hand side with respect to y. So if you integrate and simplify it by applying the limits, upper limit and the lower limit, then you will end up with this expression, q is equal to bh cube by 12 eta into dp by dx. So if you integrate with respect to y between the limit 0 to h by 2, you will be end up with this equation, q is equal to so and so, call this equation as 8. Now here it is for b, for the entire length if you consider, just replace b with capital B for the entire length. If not for the elemental length, for the entire length, replace b with capital B, q is equal to capital B into h cube divided by 12 beta into dp by dx. So this is the expression for the rate of flow in between two parallel plates. Okay. Again in this equation dp by dx is there. So if I consider dp as the pressure difference between the left hand end and at the right hand end, so if I consider the pressure at the left hand end as P1 and pressure at the right hand end as P2, the difference being P1 minus P2 for the entire length. So I can replace this dp by P1 minus P2 and dx by the entire length L, that is what written here. So dp by dx I can rewritten as P1 minus P2 by L. So equation 9 becomes q is equal to bh cube by 12 eta multiplied by P1 minus P2 divided by capital L. Okay, call this equation as 10. So you can consider this equation as the rate of flow in between two parallel plates. So these are all the formulas to be memorized to solve the numericals between the capillary tube as well as parallel plates. So this is the set of formula for the flow through capillary tube, the flow rate and the maximum velocity, and this is the set of formula to calculate the flow rate and the maximum velocity if it is flow through the parallel plates, two parallel plates. Okay. So this is for capillary tube, flow rate as well as maximum velocity. This is for flow rate as well as maximum velocity for the flow between two parallel plates. So now we will try to solve few of the numericals. So we will take up the first problem now. So the first problem starts with determine the flow through a capillary tube. So here it is a flow through a capillary tube. You need to substitute the corresponding formula. So determine flow through capillary tube of diameter 60 mm, length 3 meter. The oil used is SAE 40 at 60 degree. Okay, at the temperature 60 degree, the viscosity you need to get it from the data handbook. Okay, the pressure distribution over the length is 0.3 Newton per mm square. So pressure distribution over the length is given. Over the length means 0 to L. So it is P1 minus P2 information is given. So pressure distribution over the length means it is P1 minus P2. Okay. So if you try to collect the data, here diameter is given as 60, d is equal to 60. Now usually the viscosity will be denoted by Pascal second, PAS, Pascal second. Pascal means Newton per meter square. 1 Pascal is 1 Newton per meter square. So it will be in meters. Okay, viscosity will be in meters. Therefore, try to get all the units in meters. So 60 mm, diameter 60 mm is given. Convert this into meters. 60 into 10 power minus 3 meters. Length as given as 3 meters. So retain it as 3 meters. Oil SAE 40 at 60 degrees given. Fine. And then pressure distribution over the length. Pressure distribution over the length is given. So P1 minus P2 will be the pressure distribution over the length L. So P1 minus P2 is 0.3 Newton per mm square is given. So mm square, if you convert mm square to meter square, 10 power minus 6. If you take to the numerator, 10 power plus 6. Okay. Now, if you open your data handbook, in the figure 23 2b, page number 23.7. In that page number, if you go to the figure 23 2b, for SAE 40 at 60 degrees centigrade, you will find absolute viscosity value for this corresponding oil as eta is equal to 38 into 10 power minus 3 Pascal second. See here, this is Pascal second. Pascal means 1 Newton per meter square. This will be in meters. Therefore, I have taken all the unit in meters. Okay. So this information you need to get it from the data handbook. As I already told you, the data handbook is available at the stores, MIT stores. You can come and buy it, and you should have data handbook in your hand to solve these kind of problems. Okay. So now our intention is to determine the flow through the capillary tube. So flow through the capillary tube, the formula is given like this from the Hagen-Poiseuille law. Q is equal to pi r to the power of 4 divided by 8 eta into P1 minus P2 divided by L. So we have all the information, substitute here, pi multiplied by 30. 30 means d by 2, radius d by 2, d is given as 60, 60 by 2 it is 30. So 30 into 10 power minus 3 is the radius, r to the power of 4, r to the power of 4 divided by 8 is this one, eta obtained from the data handbook, tribology data handbook. Right here, multiplied by P1 minus P2 will be the pressure difference, distribution over the entire length. So P1 minus P2 divided by the length 3 meter. So if you calculate the value of flow rate, you will end up with Q is equal to 0.837 meter cube per second. So usually flow rate will be denoted by meter cube per second because viscosity will be in meters. Okay, so I need to get all the units in meters. So ultimate answer for this question is Q, the flow rate through a capillary tube of so and so diameter and so and so length with the so and so pressure distribution with certain oil specified. We will get flow rate as 0.837 in meter cube per second.